क्योंकि इसी से चेहरे पे, नहीं तो उससे एक्चुअली प्रॉब्लम एकदम साइड।
Okay, for information, the YouTube broadcast has started. We're gonna start in a minute, I think. Hi, Samuel. Do you want to quickly try sharing your presentation just to see if everything's working?
Oh, sure. Yeah. Visible?
Yeah, it's working.
Okay,
Thank
perfect.
you. Okay, we almost have all the speakers and it's 7:01. So I guess we can start.
Yeah, sure.
Do you want to say something, Suman? Or?
Oh, okay, fine. So thanks everyone for agreeing to be part of this particular meeting, and thanks to those particularly who are attending it in an unearthly hour right now. So we will start with Bharat, and for this particular session, Floran has kindly agreed to become the chair. So Floran, the floor is yours.
Yes,
And
thank you, Suman.
Adli, please remember to press the record button.
Just did,
Yes.
thank you.
Yes, thank you, Adeli and Suman. So I will keep track of the time for this session. So it's a very packed session. So I will remind you 3 minutes before the your time is done. So we start with Bharat. We will give an overview of the field with the title Quest for the Cosmic 21 centimeter Signal and Observer Perspective. So Bharat, it's all yours. And I will tell you 3 minutes before when the time is down.
Okay,
just
thanks, Floran.
Sorry, if I may just add, you can ask questions either here in the Q&A or on Slack. There's a thread that's dedicated to Bharat's talk. Sorry.
Okay, thanks, Laurent, Adley, and Suman. Hi, everyone. My name is Bharat Galot. I'm a postdoc at ASU working with Jet Bowman, Danny Jacobs. I'm also a part of the HERA collaboration. So today I'm going to talk about an observer's perspective of the hunt for the cosmic 21 centimeter signal, and what are the challenges we face and what techniques we usually use. Okay, so let's begin. Okay, so just a quick outline of the talk. I'll give a brief overview of why do we need to study the universe first billion years, and how do we study it using the redshifted 21 centimeter line. And we'll talk about the experiments which are aiming to probe this redshifted spectral line, as well as the techniques which we are using. Okay. So when we look at the timeline of the universe, we can see that the cosmic microwave background observations, they provide information about a certain moment of the in time when the universe was only 400,000 years old, and it does not give any evolution information. However, when we look at the nearby galaxies, galaxy clusters with with other telescopes like optical telescopes, infrared, etc., they provide a nice picture of the present day universe. However, after the last scattering surface, the universe was cold, dark, and neutral, and we do not know exactly how it actually became from being cold, dark, and neutral to warm and ionized and full of very distinct sources and galaxies. So observing these periods of dark ages and cosmic dawn and epoch of realization will actually provide a nice movie of the evolution of the universe during these epochs, basically how the baryonic and dark matter structures evolved during this first billion years of the formation of the universe. Now, there are several questions we can ask about these epochs because as I mean, it's not like we do not have any information about these epochs. There are some probes, for example, there are indirect probes such as use the Thomson scattering optical depth of using CMB observations, or the quasar high redshift quasar absorption spectrum, or observations of high redshift galaxies, etc. They give some information about when the reionization basically ended, but do not tell anything further than that. There are several questions which one can ask. For example, what was the exact timing and duration of these epochs, and what type of sources were responsible for heating the IgM or ionizing the IgM, whether they were population 3 stars or mini quasars, and when did these first stars form, and what were their properties, and what were the properties of the first galaxies which formed in the universe? For example, what was their type or size, luminosity, morphology, etc. So in order to answer these questions, we need a direct probe of these epochs. That takes me to the my next slide, that is the neutral hydrogen brightness temperature. So we can, since we know that neutral hydrogen was abundant during these epochs, we can observe the H1 brightness temperature fluctuations against the cosmic microwave background. And that itself tells us a lot of, has the potential to tell us a lot of information. For example, we can probe ionization history of the universe. We can also constrain cosmological parameters. We can study about the astrophysics of gas during that period. Also, we can study about peculiar velocities and bulk flow of baryonic and dark matter, etc. Now, there are several experiments which are aiming to measure this cosmic 21 centimeter signal. These experiments are mostly listed here. LOFAR, which is in Netherlands, MWA in Australia, Paper in South Africa, it's been decommissioned now, GMRT in India, HERA, which is being built out in South Africa, Nenufar in France, Owens Valley Long Wavelength Array in United States, and the upcoming Square Kilometer Array. So all these experiments are aiming to measure the 21 centimeter signal from the epoch of reionization as well as cosmic dawn. Now, measuring this signal is an extremely challenging task, and that's why there has, I mean, although these instruments have set very impressive limits in last decade, but there has no detection yet. So the observations of these of the 21 centimeter signal is limited by real world challenges. Because the actual signal we would like to measure is extremely faint, in order of millikelvins, whereas the contaminations in the signal are several of orders of magnitude brighter. For example, the observed signal is contaminated by astrophysical foregrounds, which are 3 to 4 orders of magnitude brighter. The signal gets distorted spatially and spectrally by the Earth's ionosphere, which makes it difficult to separate the signal from the data. The radio frequency interference from the from man-made objects, for example, radio, FM, TV, or mobile phone communication, or satellite communication also interferes with the observed data and making it extremely difficult to separate the signal. In addition to that, the instruments are also not perfect. They also have some spectral behavior, which sort of corrupts the data in some ways, and that has to be taken care of. Along with that, we have the data processing of the observed data, and the signal extraction process itself can introduce artifacts in the data in the process. Now, how do we do this signal separation? So for that, there are several techniques have been developed over several years, and these techniques can be broadly categorized into two. One is Fourier space statistics. The other one is image space statistics. So as the name says it all, that Fourier space statistics look at the data in Fourier space, whereas the image space statistics look at the data in real space. Some examples of Fourier space techniques are statistics are power spectrum, which has like several types. For example, we have imaging or map making power spectrum. We have delay power spectrum. There is multi-frequency angular power spectrum. And then we also have a bispectrum, which is a fairly recent technique and it's being like explored a lot. So two examples of them are closer phase spectrum and direct bispectrum estimates. And then we have image-based statistics, that is extracting information from the images directly, such as variance of the signal as a function of redshift or skewness or kurtosis. There are 2-point correlation statistics, which is like image-based counterpart of the power spectrum. There are 3-point correlation statistics. There are other higher, more advanced statistics. For example, we have bubble size statistics, counts, etc. There is a third category, which I have not mentioned here, that is cross correlation of the 21 centimeter observations with other probes such as CMB or high redshift galaxy surveys, etc., or other galaxy surveys. Okay, so let's start with the some Fourier space statistics. So today, for the most part, I will be focusing on the Fourier space statistics. Let's start with that. First one is the imaging power spectrum. So the interferometers measure visibilities, and these visibilities can be converted to images by Fourier transforming in sky coordinates. And another, if you take one more Fourier transform across frequency, then we end up in the Fourier space. Now, the foregrounds, the instrumental effects or mode mixing, and the signal have certain spectral behavior. And the best thing about using Fourier space is that we can exploit this spectral behavior to separate these components. For example, intrinsic foreground tend to be smooth, very smooth along frequency direction. Therefore, they always end up at lowest wave number modes. Whereas the mode mixing component has some spectral structure, therefore it spans more wider range of wave number modes, but it is these are also limited to a certain range with what we call an instrumental horizon. And then whatever the remaining region is the EoR window, which is expected to be dominated by the 21 centimeter signal and the noise. So most instruments aim to either measure the power spectrum in the EoR window, or attempt to remove these foregrounds to obtain, to measure it on other wave number modes. There is another technique similar to the imaging power spectrum, is the delay spectrum. In this one, instead of going to the image space, we just take the visibilities per baseline and Fourier transform them across along frequency and to frequency to go to the Fourier space. Now, this is mostly similar to the imaging power spectrum, but and it approximates the imaging power spectrum very well, and all the uh, all the components of the observed data, for example, the intrinsic foregrounds or the mode mixing or the 21 centimeter signal, they actually they behave very similarly in case of delay spectrum also, except for small some deviations. Now, these this was these two techniques are mostly used by the instruments, but they are used in two different ways. One is we call a foreground avoidance strategy. The other is foreground removal. In foreground avoidance strategy, what we do is we measure the 21 centimeter signal in the EoR window and do not attempt to remove any foreground. Now, there is a pro about this technique that it is an relatively easier implementation, and because we are skipping a big step of foreground removal. But there is a limitation that we are limited to a small number of Fourier modes, as well as most sometimes it requires very specific array configurations. So mostly Paper, MW, and Hera follow this strategy. Then we have foreground removal strategy, where we attempt to remove the foregrounds within the wedge to measure the 21 centimeter signal. Now, in this one, we have the pro is that we get access to a much wider um, larger number of Fourier modes, whereas the uh, biggest challenge with this technique is that the foreground removal is a non-trivial task, and sometimes, if not done carefully, may lead to signal suppression or signal loss. So the telescopes like LOFAR, ACE, NanoFAR, and future SKLO use foreground subtraction for power spectrum measurement. Okay, so moving to the next estimator, that is the multi-frequency angular power spectrum. Now, this is an alternative approach, and its formalism was provided by Datta et al. In 2007. So the MAPS estimator jointly characterizes both angular as well as spectral dependence of the signal, which we know that we have foregrounds tend to behave differently than 21 centimeter signal. So the idea behind this technique is that we can express the brightness temperature fluctuations in spherical harmonic spaces, and use those spherical harmonic basis coefficients to actually get the angular power spectrum by correlating those coefficients at different frequencies. So here is an example of different 21 centimeter, the angular power spectrum for different 21 centimeter models. And on the right one, we have a comparison for how do foregrounds look like. For example, the dot dash line, the green dot dash line is galactic synchrotron, and the dotted line is compact sources. This technique has been used in past on GMRT data. So in 2011, Ghosh et al. Used this technique to constrain neutral hydrogen fraction at post-ionization redshift of 1.32. They also use the same estimator to quantify diffuse foregrounds for the reionization redshifts, that frequencies are around 150 megahertz. However, it's their analysis was fairly straightforward. That is, you need to, of course, you need to remove the foregrounds, and for their analysis, they just did a straightforward, a 4 polynomial fit and remove that. However, that technique may have like issues such as signal loss, etc. And additionally, it is not well understood how the other contaminations, like, for example, ionospheric effects or RFI or any signal processing artifacts affect this particular estimator. So there is a need of understanding that part very well, because that, as I described earlier, it's a significant part of the signal extraction process. Okay, moving to the next statistic, that is the closer phase spectrum. So this is a very recent development. So this formalism was provided by Tyagarajan et al. In 2018 paper. So the idea is that the closer phases for a triad of antennas tend to be immune towards any antenna-based corruption. So if you look at the bispectrum phase, so bispectrum is given by this, calculated by multiplying visibilities from a triad of antennas. And if you look at the phase of that, it is independent of any phase added by instrument itself. So hence it's like, it's not significantly affected by antenna based effects, not like, and there can be like other issues which I'll discuss later that can affect this statistic also. That there can be like issues which are not like same for antennas and do not cancel out in this process. But okay, moving forward, these statistics has been looked very closely. For example, here you can see how on the top figures, you can see the visibility amplitudes for different baselines and for different types of signals. For example, the solid lines here show foregrounds, whereas the dotted lines show the fiducial EoR signal. On the right panel, you can see the corresponding bispectrum phase. So, and for the two components, so we can see that there is they are even in the bispectrum phase is also very spectrally different for the signal and the foregrounds, and this can be utilized to study the spectral signature of the cosmic 21 centimeter signal. In the bottom plots, you can see visibilities for different baselines, and the bottom plot shows the fluctuations just because of the H1 signal, and on the right side the same what's the fluctuation because of H1 on the bispectrum phase, and how does the intrinsic phase for the foregrounds look like. Now, so this technique has also been demonstrated on Hera data, where just to show an example, on the top figure, you can see the left panel. The solid lines are the foregrounds, and the dotted lines correspond to the 21 centimeter signal. For different colors are just different baselines. On the right side, you see a corresponding bispectrum phase. So this is a delay spectrum. So the idea is that since we have spectral structures in phase, we can use a delay spectrum approach to separate these, just like we do in case of normal visibilities. And we do see that there is some correspondence between the two, that there is a certain floor, and then there is width. The foregrounds tend to span a certain width, and then they also use the technique to demonstrate on the actual data. So the bottom plots here are showing the application on actual data. However, here there is a catch that uh, how there is a big catch that how do these units, or how do these spectra correspond to the physical processes happening? Because for standard delay spectrum or power spectrum, we know that we are well aware about the scales as well as the power levels and the units. Here, since we are looking at the phase, there is a need to understand how do these levels and features relate to the real physical processes. In addition to that, uh, further studies are required to understand how the systematics such as cross-coupling or reflections, etc., appear and affect the closure phase. Okay, so finally, I will talk a little bit about the image space statistics. So I'll give a quick review of the 1-point statistics. So the idea is that we can use the images from different instruments, for example, LOFAR and HERA, to and look at the variance, skewness, and kurtosis of the signal as a function of redshift to understand the history of ionization. And we can use that to constrain parameters, various parameters. However, there is a big problem that foreground mitigation or foreground subtraction is a big challenge, because images are corrupted by the foregrounds as well as instrumental effects. So one of the big challenges here also is a removal of foregrounds. So there have been like some work on like understanding how can we use these 1-point statistics in foreground avoidance scenarios. For that, you have to wait for Pianet's talk. He'll talk about it more and some with perspective of Hera. And I will stop here at the summary. So just to summarize, that the observations of the 21 centimeter signal actually promise to open a new window on the structure formation in the early universe. But these observations we are trying to do with various instruments are limited by various contaminations such as astrophysical foregrounds, ionospheric effects, etc. There are, as I discussed, there are several methods that have been developed or are being developed to statistically measure the signal, such as Fourier space statistics or image space statistics. So one of the key challenge in both of them is how do we control the foregrounds and in order to do a clean extraction. One of the key points here one of the keys to understand the efficiency of these methods and how do we do it is basically doing full propagation of sky and instrumental effects through simulations and understanding how each estimator performs. Yeah, I'll stop here.
Thank you, Bharat, for this very nice overview. So maybe we have time for 1 or 2 questions. So if somebody from the audience, I don't see any question in Slack or in the chat, but maybe if somebody has a question.
In the Slack, Pianat asked a question, I think.
Oh.
Yeah, can I just say it here?
Thread, yeah.
Yeah.
Yes.
So can you comment on the foreground mitigation strategy using M-mode power spectrum in Eastwood 2019?
I think they use some filter. I'm not like exactly sure, but it's yeah, I kind of not exactly sure. I think, but it's some sort of filter they apply in image space. I kind of don't remember the exact name of that.
So it's basically a variant of foreground subtractions, correct?
Okay, thanks.
Okay, maybe just time for one more question. If somebody has. Otherwise, I will ask just one quick question about the closure phase spectrum. I think it looks like a quite promising estimator. So what do you think about the impact of the can it help in solving the problem with contaminants, the closure phase spectrum?
So it does. I mean, you do get rid of course, for example, let's say antenna base effect. For example, you have I can think of like any direction independent effects would be removed, but when however, there can be like other problems, for example, which are more complicated and then start to change with direction as well as from antenna to antenna, then you start to have issues.
Yeah. Okay. Well, thank you. Thanks a lot, Bharat, again. And we'll move to the next speaker, Samuel.
Thanks, everyone.
I think you need to, yes.
Okay, so I'll go ahead and share.
Share the screen. Yes.
Yeah. Okay. Is this visible? And if I go full screen, is it good?
Yes, that's perfect. That's
Excellent.
wonderful.
Okay. So I'm a.
Yeah, go ahead.
Okay. Great. There was an echo for a moment. I'm a master's student at Bishop's University. And so I'll just jump right into learning around galactic foregrounds. So sort of the object which we are interested in is this H1 21 centimeter signal from like reionization era redshifts. So redshifts around 10 up through 20, that sort of era. And we're trying to probe that era for the highly redshifted 21 centimeter signal. As we saw in the last talk, one of the huge obstacles to get in you have to get over in order to actually make a measurement of that signal are these galactic foregrounds. And I really like this figure here because it shows this little medieval observer. And in the Middle Ages, the firmament is this barrier between the material and heavenly worlds. And so in our age, we do have our own firmament in the form of this galactic overwhelming foreground. It's 10 to the 5 times brighter, greater in magnitude at our target frequencies than our target signal. And so it creates this kind of a insurmountable barrier, which just obfuscates the entire signal. Lucky for us, this foreground is predictable. This is a really great figure from a Pober paper, 2014, which shows us in cylindrical Fourier space, sort of the blueprint or the footprint of the galactic emission. And so in this figure on the right, I show that the galactic emission is sort of contained here in this wedge and intrinsic foregrounds region along the perpendicular K modes in the sky plane. Whereas in this region, which is called the EoR window, those Fourier modes should be mostly free of contamination from galactic and extragalactic sources. So the end goal of this research project is to take advantage of the wedge in order to perform foreground recovery rather than foreground subtraction. So what's the nuance here? What's the difference? In a foreground subtraction model, you have essentially two humongous numbers. One number is the signal plus the huge noise, and then the other number is your perfectly calculated noise, which you will then subtract out and then produce your signal beneath it, which is, once again, much smaller and very specific. You have to get the model of the galaxy just right for that to work. So we're not doing that. We're doing so-called recovery, where we're just going to throw away any data that we think has noise in it, just throw it out. And then based on what's left, we're going to reconstruct what we threw out. And so why is that reasonable? Why is that possible? We'll get into that. So, as many are aware, we don't have good tomography image data from the reionization period. So we use simulations from 21CM FAST. It's from the Messenger et al. Group. And so this is sort of the kind of basic, it's a semi-analytic, it's fairly cheap to run. And so you need lots of data in order to do machine learning, and doing those gigantic hydrological simulations would not be efficient or a good use of time. And so just to really illustrate the effect of the wedge of the Milky Way foregrounds is, so if I take the Fourier transform of this simulated map and then just zero out all of the wedge modes, all the modes that exist in this wedge region, I just send them all to zero, and then inverse Fourier transform back to real space, I end up with this picture here on the right. Nothing of interest or value remains. You're just throwing out so much data that whatever's left is there's nothing visibly interesting there. So let's get into the kind of the reasoning behind why you can do foreground recovery as it is. And the reason is that the 21 centimeter signal is expected to be non-Gaussian. And so on the left, this is just a very simple diagram of, let's say, a Gaussian distribution of vectors, where the vectors have random magnitudes and random phases. In a non-Gaussian distribution, you have potentially random magnitudes, but there's some correlation between their phases. So here there's a very clear pattern with the magnitudes and the phases. On the left, there is no pattern. If I were to remove one vector from each distribution and tell you to guess, okay, now add in the missing vector, you can do it for the right because it's non-Gaussian and you see the pattern. On the left, you could do no such thing if you didn't know what the original image was. So this is a really simple version of the philosophy behind this project. Hey, well, if it's a non-Gaussian signal, I can throw away an arbitrary number of vectors, and as long as I have a few left over, I can kind of figure out that covariance matrix and reconstruct all of the missing vectors that I threw away. So how do you solve it? This is sort of the Hail Mary of physics is the neural network. You just throw it at machine learning. If you don't have an explicit mathematical solution, or it's a nonlinear regression problem. There are reasons to do machine learning, but that's what we go for. So this is sort of the very simple. This is the idea. We're going to throw in wedge affected images like this one on the left, and the idea is to allow the network to get to a point where we can just see that and then map right back to a non-wedge affected version. And so just to kind of connect with the last talk, okay, this is sort of the, an underlying message here is that this is a image space sort of problem. He talked about Fourier space problems you can do and image space problems, and there are, say, 2-point, 3-point statistics, there's mapping. This falls under the image space sort of problem solving type of project. So, one thing neural networks are great at is image segmentation, where I throw a picture at it and it says, okay, well, all these pixels here, that's a bicycle, or that's this or that. And so we just turn this into a classification task where you say, okay, take every pixel and tell me if it's ionized or neutral. And here ionized means fully ionized, and anything less than that is just considered neutral for the sake of this classification. Okay. So we have data set from various neutral fractions. spanning redshift 7.85 through 8.5. And I'll just show you right ahead the results, and they're very promising. So if you look on the far right here, that is a wedge affected image, which is passed into the network. It's associated, if it were not affected by the wedge, with the image on the far left. If I were to binarize that image, that's this binary mask in the middle left, and then the middle right is actually what the network predicts. And this is not an image that it was trained on. This is sort of what's called like a validation image. So it's able to produce that from the image on the right. So we up the ante a bit, simulate some instrumental noise for Hera and SKA, and we find that even for Hera and SKA, I mean, this is on the image on the right, this far right here, that's the wedge plus Hera instrumental noise affecting that, and it is still able to reconstruct some kind of bubble distribution, and similarly good, if not better, results for the SKA. So we run it through a null test, make sure, okay, is it really exploiting non-Gaussianity here? In order to test that, we Gaussianize a map where we transform it to Fourier space and then randomize the phases of each Fourier vector. If the Fourier vectors have a random phase, then there's no longer going to be that covariance matrix, and it should fail. And indeed, the network does fail to reconstruct anything when we Gaussianize the map. So yeah, just works. It seems to be working pretty well, and this is kind of an avenue of continued work and exactly quantifying what are the limits of this at what redshifts, and what else can be done with this kind of a project. And so I think I'll just open it up to questions right now.
Thank you, Samuel. Actually, we will keep the question for the discussion session. So if you have any question for Samuel, you can just write it down on Slack or keep it for later. And we'll move straight away to the next talk by Payanat. I'm sorry if I don't pronounce the name correctly. We will talk about 1-point statistics and especially for ERA. Go ahead.
Yeah, thanks, Florence. Hi, everyone. My name is Pianat. I'm a postdoc at UKZN in South Africa. And today I'm going to be talking to you about my work on 21 centimeter 1-point statistic, which I mostly did during my PhD at Arizona State University with Judd Bowman and Danny Jacobs. Excuse me if there's a noise coming up. Since we just heard a nice overview from Bharat, I'm just going to jump right into the problems. There you go. So as Sam just mentioned earlier, the 21 centimeter intensity fluctuation fields is non-Gaussian. But the problem is that power spectrum, which most of the experiments are aiming to measure, is only sensitive to Gaussian signals. One way to understand this is through the examples that I have here. On the left, you have a slide from semi-analytic simulation from Adam List. This is an EoR signal, and you can see the ionized bubbles here and there. They have sharp edges. And then on the right, I take the image on the left for a transform it, shuffling the phase portions, kind of like similar to what Sam just mentioned. And for a transform back, then you kind of randomize the signal here. These two maps have exactly the same power spectrum. So what this means is that either signal can result in the same power spectrum as the EoR, and saying in a different way, power spectrum cannot give you information on the non-Gaussianity. And to have that information, you need to look at other statistics. And one of the most simplest statistics that you can use to look at non-Gaussianity is the probability distribution function, the PDF, and its 1-point statistic. PDF is, simply speaking, from observational perspective, it's just a histogram of the intensity fluctuation maps normalized to an integral 1. Then 1-point statistic, it's kind of like a collective term that appear in literature often, but we are probably familiar with it. You probably heard of the variance skewness and perhaps kurtosis before. These are what we call one-point statistic. And in principle, they are shape parameters of the PDF where the variant describes the spread, skewness describes the symmetry, and kurtosis describes the tailness. So let's just go into a little bit of the detail here. Skewness describes the symmetry in a way that the PDF would have a positive skewness if the distribution is leaning toward the right, or in the same way it has a long right tail, and negative skewness means the long left tail. Kurtosis would be positive if the distribution have more tail than the peak, and vice versa. And just for a node, a perfect Gaussian distribution have zero skewness and kurtosis. And in statistics, these are simply the standardized moments, statistical moment of the signal. So let's put these into the context of reionization signals. Here you have a map of the early state of reionization, 30% ionized, and you can see that the distribution is mostly Gaussian-like with small bubbles starting to form. These give rise to a Gaussian-like PDF with a long tail toward the left, and so the skewness would be negative here, will be positive here, excuse me. Oops. And during the middle of reionization, ionized bubbles starting to form. These add into the peak at the zero of the distribution, so the PDF become bimodal. And near the end of reionization, since most of the pixels are ionized, you have a lot of zeros, so you have a strong delta-like peak at zero with a long tail to the right. All of these together give you some sort of the picture like this. The reionization evolved from Gaussian-like field to very, very non-Gaussians, and the PDF changed from Gaussian light to bimodal to delta light functions, and these give rise to a very unique evolution of variance skewness and kurtosis. The variance will peak during the middle of realizations. Kurtosis will have this negative dip very interestingly near when the PDF become bimodal, and skewness would evolve from negative with the long tail to the left to positive with the long tail to the right. And the work that I did during my PhD is to develop a realistic mock observation pipeline for Hera to forecast if we can make measurements of these statistics with Hera. I don't have time to go into the detail of this, but I just want to point out that in this result that I will be showing, there is no foreground. So we assume perfect foreground removal. Let's jump right into the result. Here on the left panel, from top to the bottom is variance, skewness, and kurtosis. Different color and light is the different build-out stages of Hera, and I want to bring your attention to the solid purple light, which is the complete Hera array. And on the right panel is the 1 sigma signal-to-noise ratios that we take into account thermal noise and sample variance. And you can see that Hera should be able to detect these statistics near the end of realizations if foreground can be removed. And that is a big if, right? Because we know that it's caused a lot of problems. So what do we do? Well, what I've been doing since then is trying to figure out if we can still measure this statistic in foreground avoidance regimes, as Sam's and Dara just mentioned. The foregrounds are confined within the wedge-shaped regions inside the Fourier transform K space. So, and we can use only the data inside the foreground free, in principle, EoR window to do data analysis, and that would be making measurement in foreground avoidance. So what we did was we take the output from our previous pipeline, which take 21 centimeter simulation cube and do some gridding to form a full sky model and smoothing, and you get these maps that we make a measurement. So with this map, you can stack it into an image cube and FT into K space. And then since we know exactly where the EoR, where the foreground wedge is in the K space, we can form a foreground filter or a wedge cut filter cube, multiply with the Fourier data cube, FT back, and you get a foreground wedge cut image that you can make a measurement. So we've done a Monte Carlo simulation of these with 500 noise cube per signal field, 20 field to mimic the sky coverage of Hera, 500 filter parameters. Filter parameters here mean we experiment with the different extents of the foreground wedge, and you see here the leakage from window function. When you do FT, you usually apply window function to improve the dynamic range, and usually that causes the leakage of the foreground outside beyond the theoretical foreground wedge. And we found that doing a rolling style filtering worked best, where you take a small chunk of the data, apply a wedge cut filter, then we keep the central slice, which we found have the least bias, and then you roll these filters up, and eventually you can just stitch the central slices together to form these output cube that we make the measurement. And these are the result. The left panel has no filter, and on the right 4 is where some filtering happening. The horizon is where the full foreground wedge happening. The rightmost is where we take extra into account the extra leakage that could happen. And here's the statistic. I'm just going to show skewness and kurtosis. There's a lot of information here, but just looking at the top row, where that would be the most realistic case that we could do. If you can control no leakage, meaning if you can make it somehow the leakage disappear, you can definitely, it looks like Hera should be able to measure this statistic, especially near the end of realizations. With some small leakage, maybe you can recover something. And the same idea apply, the same pictures apply to kurtosis. What this means, what this implies that the non-Gaussian signal live in the lower K where the foreground get cut out. And it's look like if you cut the wedge, it's remove the signal, but the noise is not cut out. So how can, if we want to measure it, we either need to reduce the noise with the longer integration time or more binding, or try to figure out how to mitigate the foreground leakage outside of the wedge. So in summary, can we measure one-part statistic? Well, in optimistic sense, Hera should have enough sensitivity if we can mitigate the foreground, and that is a big if. But the question that I think I want to raise to the audience and the panelists here is it really worth to do this measurement? We have limited resources in humans, and if you work on data analysis, you know that power spectrum measurement is hard enough. So can we learn more astrophysics from measuring one-point statistic and also other statistics? And that is the end of my talk. Thank you.
Thanks a lot, Payanat. So again, if you have questions for Payanat, you can ask them on Slack. I see that you have a question yourself in your summary, and that would be a nice input for this discussion session as well. So, and we will move straight away to the next talk by Yu-Yin. Yes, we talk about excess noise, exploring source of excess noise with LOFA. So go ahead.
Okay. Hi, everybody, and thanks for giving me the opportunity to present our work here. I am Yu-Yin Gan from Kaptein Astronomical Institute in Groningen, the Netherlands. And today I am going to talk about sources of excess noise in detecting the 21 centimeter signal with the LOFA instrument. So previously, Bharat has introduced a lot of observation techniques. So here I will skip the background, and I will directly go into the challenges we face in LOFA EoR project. And as other speakers mentioned earlier, that the problem of observing the 21 centimeter signal is that the observed data does not only have the 21 centimeter signal that we would like to observe, but on top of that, we have astrophysical foregrounds, which are 3 to 5 orders of magnitude stronger than the EoR signal. But also we have ionospheric effects, which impact the power and the phase of the signal. And further, the signal is distorted by instrumental effects. And also there's radio frequency interference when we observe the signal. So there are some human activities which actually use the same frequency band that we are using for observing our data. So to be able to extract the 21 centimeter signal from the combination of these different components is very difficult. And the solution is to calibrate the data. So we have to understand those non-signal effects, and then we have to model them, and we finally want to calibrate those things, so remove them from our data accurately. So we have developed a pipeline for doing this calibration job in LoFar EoR project. And of course, after we have run the pipeline, we would like to know how well we have done the job. And there are many ways of measure the quality of the calibration. And one way of doing it in LoFar EoR is to look at the ratio between the residual and the estimated noise in the 21 centimeter power spectrum. So here we have one plot which presents the ratio of the residual and the estimated noise. And I took this one from our latest upper limit paper, which is published last year by Mertens et al. And ideally, if the calibration did a good job, the ratio between the residual and the estimated noise should be close to 1. However, in reality, as you can see from this plot, that the ratio is higher than 1. And especially in the foreground wedges, where K parallel is smaller than 0.4, we actually see higher ratio here. So it could even reach 7, and yeah, this is very high. And this extra noise above the estimated thermal noise is known as the excess variance in LoFar EoR. So before we even talk about detecting any kind of signal, it is important to first understand this excess variance, and then we want to identify where actually it comes from. And further in the future, we would like to, of course, reduce this excess variance. So here in this work, we focus on finding the possible sources of the excess variance. So of course, we know that the calibration is not perfect, and there are some errors in that. And there are some candidates that we think probably the reasons for the excess variance. And this could be some residual foregrounds that we did not completely remove during the calibration. And this could be the sky model that we are using is not complete. And it could also be that the rapidly varying ionospheric effects that we did not take into account when we calibrate the data. And also there could also be some alpha that we did not flag properly when we are processing the data. So here we want to identify those sources and how much they contribute to the excess variance by looking at the correlations. And we focus mainly on the first 2 candidates, so the sky effect and the ionospheric effect. So here I'm going to show some results that we have. So first of all, we have the correlation plots for the excess variance and local site real time. So here, what we wanted to see was the correlation between the excess variance and the sky model. However, it is kind of difficult to directly look at the correlation between the sky model and the excess variance. For this reason, we choose local site real time as a parameter to indirectly look at the correlation. So we know that if you fix local site real time, that means that, given local site real time, that the instrument is always seeing the same part of the sky. So you kind of fix your sky model for this specific time slice. And we took 13 nights of observation from our LOFAR data. And then we slice each observation into 3-hour LST slice. And for each slice and each observation, we estimated one power spectrum. And then we average, we average over K, and we plot the excess variance as a function of local site real time. And it was interesting that we actually see a clear LST dependency here. So for all the observations we have considered here, they always show the lowest excess variance in LST 3 to 6. So with this, we conclude that the excess variance is correlated to local site real time, and probably for this reason also to the sky model. And to further, if this is true or not, we simulate visibilities based on the sky model. And we do the same exercise. And interestingly, in the simulated Stokes eye power, we see a very similar LST dependence. And with this, we conclude that the excess variance is actually related to the sky model. And then additionally, we also looked at the correlation between the excess variance and the ionosphere. And here we took the diffractive scale as a measure for the ionosphere quality. So there is so this by definition is the length scale where the phase variance is 1 squared radius. So what you have to remember is that higher diffractive scale means better ionosphere quality. However, when you look at the plot, you see that for a given excess variance, for example, here around 2, you can have a low value of diffractive scale, can also have a higher value as well. So it's pretty much randomly distributed. And then we see that there's no strong correlation, which was kind of surprise to us. So it seems like that the excess variance is more likely to correlate with the sky-related effects, such as the sky model, than the ionosphere. And in the future, we would like to, of course, combine more data. And so far, we have done analysis pretty much by hand, manually plotting A against B. And in the future, we would like to add more data in and apply some machine learning techniques to find correlations more quickly and automatically. So that's about it. And thank you for your attention.
Thanks a lot, Yin. So again, if you have questions for Yin, you can write it down on Zoom also in Q&A or in Slack, and we can discuss that in the discussion session. So thanks again for all the speakers for this first session. We will have a short coffee break now, and we will meet again in about 10 minutes. Okay, for everyone. See you.
Hey, Adeli.
Hello.
Yeah, I arrived a few minutes late, sorry.
No worries, no worries. There's the break to check.
Hi, Isabella.
Hello. Okay. Indeed, it was a good idea because I lost track of.
You lost your presentation?
Yeah, it opened it. Okay. What about now? Can you see it?
No.
Now you see it.
Yes.
And if I go full screen?
We can see the timer.
Okay, which it was not supposed to be.
I think we
Yeah,
see
we
the
see the
presenter view.
speaker's view. Yeah.
Yeah.
There we don't. Yeah.
Ah, okay, so I need to switch. Let me try again. Now you see what?
Just the slides.
Okay, great. I learned.
Keynote has a new feature, by the way, that I find useful, where you present in a window and then Zoom shares it more
And that's it.
naturally.
Yeah, maybe I should do that instead of sharing.
Sometimes you tell Zoom to share your screen and it's not really sure which one it's going to share.
Yeah. Sometimes I lose control of what Zoom is sharing.
Did you find a way to keep the presenter view, but people just see your slides? Because I've been looking for one.
I think the way it's
with
what
one screen,
Josh is, yeah, the way to do
That's
it is
Keynote,
what Josh is proposing.
That doesn't give you the presenter view my way.
Ah,
but
okay.
That's the trade-off.
Yeah, double screens for that.
By the way, it's impressive. What time is it now in wherever you are in US?
It is 12 a.m.
Wow.
So it's not that bad in California. But I will probably not be attending the next session, which I think is at 4 in the morning.
Okay.
Maybe I'll check it out on YouTube afterwards.
Yeah, Florent, I don't know if you noticed when you said that the questions were during the discussion session, that Samuel's face just, he got really worried because where he is, it was 2 a.m. in the morning.
Oh, yes.
So I don't think he's going to make it.
Yeah. But I see that there is a lot of activity in Slack, so that's nice.
Yeah, that should work fine.
Yeah, I think rather than using this Q&A section, if we push all the questions to Slack, that would be better, maybe, because then we can retain all the questions and the speakers can answer later on as well. Yeah.
Indeed.
Arnav is being asked to be promoted to a panelist.
You have been trying to do it for 10 minutes, but for whatever reason, it's not working. But thanks for pointing out, Josh.
Don't think I have that power.
Right, maybe should we start again or wait a few minutes?
I guess most of the people are back, more or less. Yeah. Ornam probably will join after a few minutes.
Okay. Well, let's start, I think. Okay, so now we'll thanks again to join again, and we will have Josh Dylan, who will talk about calibration and foreground mitigation for EoR. So the floor is yours.
Sure. Thank you, Florent, and thank you to the organizers for putting this all together. And everyone can hear me, right? Yeah. So, and thank you as well to Bharat and the other speakers who gave a nice introduction. So I'm going to go right into talking about Hera specifically. So this is what Hera looks like, or will look like. This is, as I said, the Hydrogen Epoch of Reionization Array, which we've heard a bit before. And that's a collaboration of institutions across the United States and in Africa and in Europe. And we're funded by the Gordon Betty Moore Foundation and the National Science Foundation. And this picture of Hera doesn't give you a real sense of the scale. Hera is huge. And that's in part because the 21 centimeter signal is so faint. So we need a lot of collecting area, a lot of sensitivity, but it's going to be made of 350 of these dishes. And we get that sensitivity in part by building out of relatively cheap materials. This thing is made of telephone poles and PVC pipe and chicken wire mesh. But the biggest challenge, as has been sort of discussed throughout this session, is the foreground problem. So we're interested in the 21 centimeter signal from neutron and hydrogen in the early universe. It's coming to our telescope. And in between is all of this stuff, our galaxy and other galaxies that are emitting, for the most part, smooth spectrum foreground synchrotron radiation, which, while it's 4 to 5 orders of magnitude brighter than the signal we're looking for, the 21 centimeter interferometric signal, it is quite spectrally smooth. So any attempt, whether it's foreground subtraction or foreground avoidance, is predicated on the idea that the foregrounds are smooth and you're trying to remove the smooth thing to measure something that is spectrally complicated. But of course, foregrounds and systematics are intimately tied. And part that the reason that won't work is because of calibration. So the thing we measure, this quantity called the visibility, and it depends on both of the antennas involved in the particular measurement. A baseline is what we call that, and it depends in particular on some direction dependent terms, but also here these direction independent gains. It's a complex frequency dependent number. And if these things are not properly accounted for, you can introduce spectral structure that wasn't there in the original measurement and ruin that smoothness, which was the key to separation. Now, Hera is predicated on the idea of using what we call redundant baseline calibration. The idea is that by building a highly redundant array, we're measuring the same pairs of antennas, the same modes on the sky, and therefore the same baselines over and over and over. And so what we're effectively doing is building up a big linear system. So we have 320 in the core antenna gains and 1,500 unique visibilities, but 51,000 total measurements because we're measuring the same number over and over and over. And so what we can do is just basically minimize chi-square. We can write down a model, and we have a model for our unique visibilities and for our gains. We try to solve for those simultaneously, and we want to make sure that that is as close to the data as possible given the noise. And we can actually quantify the degree to which it is a reasonable model or close to the data by writing down a chi-squared per degree of freedom in a sort of standard statistical sense. In the simulations, our code works quite well. We put in something that is purely redundant up to some noise level, and we get back out precisely what we expect, which is that the chi-squared per degree of freedom is 1. In a simulation, the model was perfect. And in practice, this actually is looking pretty good. So here's a bunch of visibilities. These are what we call waterfalls. So it's time on the y-axis and frequency on the x-axis. And all of these are baseline antenna pairs, baselines that are supposed to be measuring the same thing. And quite clearly, they're not. So the process of calibration involves first out throwing away any bad antennas. So antenna 50 never worked. Then we want to actually pose this redundancy constraint, and that lets us solve for all the gains simultaneously. And now these start to look actually quite similar. We want to remove the radio frequency interference, which is a long topic that I could go into it. But basically, you want to flag out the parts where there's bright terrestrial and human-made radio frequency interference. And then finally, we fix to an absolute sky reference. So we only have to solve for a handful of numbers, which is a very different calibration problem than what faces, for example, MWA or LOFAR. So that involves actually doing the sort of traditional radio interferometry where we make a map of the sky. These are not particularly great maps because Hera is not designed as an imaging telescope, but we can make a map of the sky and calibrate it, and our residuals look pretty good to sub 10% levels in terms of our overall calibration. So what this is then, once we have these calibrations, now we can actually compare different days to each other. So the instrument is actually looking quite stable from day to day. And so we can look at one baseline on one particular JD, and we can integrate down and look at it as we sum together 18 different days. And it really just looks like the noise is integrating down and things actually look pretty good. So we're not just interested in the visibilities themselves. We want to start forming power spectra because this is the quantity we want to use to compare to theory. So here's a very preliminary example, but here's sort of what this looks like is we have sort of some expected noise level, and we have lots of different individual power spectra that are supposed to be measuring the same Fourier mode. And as we start integrating down deeper, we're getting, for the most part, modes that are consistent with noise with some systematic here. And this is with 18 nights of data and just a handful of baselines. And if we then apply a number of techniques, which I'd be happy to talk about in more detail or point you to the papers, where we can actually start identifying that systematic that was living around K of plus or minus 0.5, we're actually able to remove that in a way that is relatively lossless. And so we're getting pretty close to our thermal noise limit on this data, which is about 50 antennas on 18 nights of data. And therefore, we're getting very close to publishing some upper limits. And before we do that, what we really want to do is build confidence that our upper limits actually are, that we actually understand the effects that are going in, and that we can really confidently say that our upper limits mean what they say they mean. So as an example, and we've looked at many different things, but I wanted to work through one of these, is that Hera is not a simple instrument. And so it will be non-redundant at some level, and our measurements are generally involve combining quantities that we say are supposed to be redundant. So one way to quantify that non-redundancy is actually to look at this chi-squared quantity. You try to make the array as redundant as possible, but you will always fail because it is not quite redundant. And so you can compare statistically the distribution here to what you'd expect theoretically. And we're seeing very strong evidence for slight non-redundancies. Non-redundancy at the sort of 10-ish% level, but clear non-redundancy. Our antennas differ from each other. They're not perfectly placed. They're, the feeds which are suspended at the focus of the dish may not all be in exactly the same place, etc. But we could use this in a number of different ways. One, we can break it down by antenna, and we can actually look for antennas that are strong outliers in this chi-squared quantity. So here, for example, antennas 98 and 136 were particularly strong outliers across the spectrum in this chi-squared broken down by antenna. And so we use that actually to pick out the antennas that we felt were the most redundant with each other. We picked out we threw out the outliers and kept the median distribution. And so the one result of that is now we can actually go and calculate to what extent is this the fact that we're measuring the same thing over and over, but we're not actually, what kind of decoherence is that creating? Because if you're combining quantities that are supposed to be the same but aren't quite the same, they will average down a little bit, and that will lose signal. And what we're seeing in our metric for decoherence is something like a 5-ish% decoherence. And so this is all going into a preliminary, a power spectrum measurement, which I can't show you the actual numbers on quite yet because we're not done checking all the boxes. We've already published these papers on redundant calibration, absolute calibration, reflection, and crosstalk systematics. And now we're preparing a final sort of push, a suite of papers on how we're estimating our error bars, how we are, our upper limits themselves, our validation of the pipeline on entirely simulated data, and then how we're interpreting that cosmologically. So look forward for that later this year. Now, in addition to those 18 days, we've also got over 100 days in the can from Hera phase 1. And meanwhile, that instrument is in some sense gone. We kept the dishes, but the entire digital system and the feeds are completely replaced. In particular, we're replacing them with these broadband Vivaldi feeds that let us go out to redshift 29. Although perhaps we won't make a measurement out to 29. And that will actually be, once we get down from about 50 antennas to about the 300 that we're designed to do, we will have way more sensitivity to basically any cosmological signal, not just at EoR redshifts, but also these epoch of X-ray heating cosmic dawn redshifts. And if, for example, the edges detection is correct, that should also raise up the amplitude of the signal around redshift 17 interferometrically, which we should be able to see. But in the EoR, which I think is the interest of a lot of folks here, this should let us really precisely constrain the ionization history of the universe. So with the sort of fiducial Hera measurement, we should be able to really knock out this question of how did reionization proceed. We're also, as we're sort of getting this new instrument ready, we're using these quantities like chi-squared as a real-time diagnostic. So we built out this redundant calibration into our real-time system so that we can understand within a day which antennas are working and why are things going wrong. And you look at all of this and you wonder, what is all of this? Some of this is radio frequency interference. Some of this I'm not sure yet. Some of this is effects of the sky, but it's a lot of things that we have to go through and sort of use this to diagnose how our system is operating. So to sum up, I've said that Hera is a purpose-built 21 centimeter experiment. It's really designed to do this one thing. And we have, from the get-go, this robust calibration and systematics control and redundant calibration. It's all part of the design. And we're now building out to a very, very large array. This thing will be as big as Arecibo was. And we're putting now the finishing touches on this suite of papers supporting our first upper limits, which should be deep enough to actually say something about the physics of the IGM at that time. Though it'll be ruling out models that probably nobody believed in anyway, but that's the place you have to start. And in time, we should be able to follow up edges and also very precisely constrain the epoch of reionization with the power spectra coming out of the full Hera system, which we hope to see in the next couple of years. So with that, thank you so much.
Thanks a lot, Josh. Very nice talk. Again, if you have questions, you can ask them on Slack, and we will move straight away to our next speaker, which will be Arnab Chakraborty, who will talk about first upper limit from the post-war period using upgraded GMRT. So the floor is yours.
Hello everyone, I am Arnab Chakraborty. I am final year PhD student at IIT Indore. I will be talking about our recent result on upper limit on post-EoR H1 signal using UGMRT at redshift 1.96 to 3.58. So there are other members also across India who are part of this observational project. And we observe LS North 1 field after the upgradation of GMRT. The reason behind the choice of this field is that it is high up in the galactic latitude. So the expected galactic synchronous emission will be less in this field, and it is also up during the observation cycle back in 2017 and in the night time, so that the effect of RFI and ionospheric perturbation will be also less. We observed it in 200 megahertz bandwidth starting from 300 to 500 and with 2-second correlation time, indication time, and 8K channels, which result into 24 kilohertz. So after first round of flagging using EO flagger, we developed a modified strategy for EO flagger for this particular observation. And after flagging it, we averaged it to 8 seconds, but we did not average along the frequency axis, so to get the best resolution along the line of sight modes. This is we developed a simple direction independent calibration pipeline. This is the image of LS North 1 field where we only perform direction independent phase only self calibration. We have not performed any amplitude calibration, or also direction dependent calibration is not being applied here. And during the calibration, we only choose the during the self calibration we choose the baseline above 1.5 kilolambda, so that no diffuse emission propagate into our model. And after getting the image, we have subtracted the 4,000 bright compact sources from our field of view, and we take the residual dataset to estimate the H1 power spectrum. So this is the only subtraction we have made during our entire analysis. There is no other thing we have done here. For the foreground, we employed a simple foreground avoidance technique where we know that the foreground is coupled with the chromatic instrument response within a wedge-shaped region, and the H1 signal is being searched for at the outside the horizon limit, and this is being applied or used for MW and Hera pipeline, and we tried to incorporate the same philosophy here for UGMRT dataset for the post-EoR H1 signal also. And for the power spectral estimation, we measured the visibility, which is the Fourier conjugate of the sky brightness fluctuation. And one needs to go to the delay domain using a simple Fourier transform along the frequency axis, where S nu is the sample weights here, which encodes the flagging, that is it is 1 and 0 for the flag for the non-flagged and flagged channels, and W nu is the spectral tapering function to mitigate the effects due to the finite band shape. And then one can do the simple visibility correlation to estimate the power spectrum after proper scaling factor, and then use the 2D power spectrum, and then one can average the modes spherically and get the 3-dimensional power spectrum. However, there are one caveat is that we cannot do the simple Fourier transform along frequency axis because there are flagging. These yellow lines are the flag region for a particular baseline here. I am showing here, and this is the output of EO flagger. So if I do the Fourier transform on the frequency, there will be the foreground leakage into the EoR window. So your window will be corrupted. So this can be thought of as a convolution of the delay space PSA, which is this quantity here. convolve with the visibility in the delay space. So we incorporated the simple clean algorithm to deconvolve this delay space PSF that is written here, which is a Fourier transform of the product S nu and W nu. W nu is your spectral tapering function. We used Blackman-Harris here, and S nu is your sampling function. So this is a simple example with a simulated visibility. We can see that if we simply use the Blackman-Harris window, there will be and there are 15% channels are being flagged, and we go to the delay space spectrum, and we see that there is a significant spillover of foreground when we use simple Blackman-Harris. But when you do the clean algorithm applied in the delay space and deconvolve the delay space PSF, then we can go to the no RFI scenario, the label to the no RFI scenario. So this is being applied to our data set. And then there is another problem, which is the visibility has a positive noise bias here. So if we do the simple visibility correlation, that will give you extra bias here in your measure power spectrum, which is coming basically due to the noise. So what we incorporate that we correlate the visibilities which falls within a UV cell, whose dimension is inversely proportional to the primary beam. So the underlying assumption is that the signal is correlated within that UV cell among the visibilities. So we create a correlation matrix for each UV cell, and whose diagonal element are the self correlation, and the off diagonal elements are the correlation among the visibilities. And that will we will take that off diagonal element to code the value of the power spectrum at that particular UV cell. And this is being proposed long back by Bharadwaj and Shetty, almost 20 years back. We incorporate the same philosophy here. And then we choose 4 8 mega chunks, which are relatively free of RFI. And we estimate we process those data set in our pipeline. And this is the 2D power spectrum of a 8 mega subband around redshift 3.58. And as we can see that there are foregrounds which are mostly contained within a wedge shape region. The black line is the horizontal line, and we choose the white the modes inside this white dashed region to estimate to spherically average those modes to get the three-dimensional power spectrum. So uncertainty in the power spectrum that comes because of the noise power. And in the right panel here, you see that this is taken from Liu et al. 2014. This is the square root of the diagonal element of the EoR covariance matrix. As you can see that it has a term, not only the thermal noise, it also has a foreground contribution here. And this equation is taken from Kolobanis et al. Who shows that there is a coupled term, which is the uncertainty due to the foreground and noise, and there is another noise term. So within this horizon limit, the uncertainty is dominated by the foreground covariance, and outside that it is dominated by mostly thermal noise. And we also found this is a noise power spectrum from the similar figure here also. This is for our observed data set. And we also found that above the higher delay modes or higher k parallel mode, this is mostly consistent with the thermal noise. So we choose those values to code the uncertainty in the power spectrum.
Yes,
this is a three-dimensional power spectrum, and this is the theoretical thermal noise limit. We see that we are more or less close to the theoretical thermal noise limit. However, we are almost 3 orders of magnitude higher than the H1 predicted power spectrum at this redshift. And then we checked upon integrating the signal coherently in the UV domain, whether we get a systematic decrease in the power spectrum or not. And we see that this is always these also follow the expected trend in the decrease in power spectrum. Then we do the jackknife test also, that is we divided the band for 4 mega chunks, and we found that it is also consistent with our theoretical expectation. And then we choose 3 others 8 mega subband at redshift 1.96, 2.19, and 2.62. And for all the upper panel shows you the 2-dimensional power spectrum. The lower panel is the 3-dimensional power spectrum after averaging the modes within the clean region. And we find that we are more or less close to the thermal noise limit. However, still there are some residual systematics left in our data set, which needs to be taken care of in our next analysis. And here it is the expected here is the estimated upper limit at redshift as a function of redshift at k equals to 1 MPC inverse. And as we see that we are still 3 orders of magnitude higher than the expected H1 power spectrum. This is only 13 hours of on-source data. before flagging. So we see that we got a fairly good upper limit for this using this data set. And then we try to find out what is the physical parameter. Omega H1 is the H1 mass density. BH1 is the bias to the underlying dark matter density power spectrum. So PDM is being calculated using CAM code, and we have an upper limit on the H1 power spectrum at different redshift. So we try to find out what is the value of omega VH1 and omega H1 and BH1. So B is close to 1 in this regime. And so omega H1 omega H1 is of the order of 0.09011 kind of thing. And as we can see in the bottom planet, it is a value of omega H1 as a function of redshift Z, where we see that there are different values based on DLA survey and local H1 survey and etc. And we see that we are still almost 2 orders of magnitude higher than this expected value from the other probes. And then for the last thing, what we have not done, whether there are any signal loss or not. So we have not done any kind of modeling and subtracted from our Stokes power spectrum. So we have not performed any kind of subtraction in our entire panel analysis. We have not performed any kind of weighting by the inverse covariance matrix in our analysis. Also, the foreground is not being filtered here. We just use the foreground avoidance technique. So we do not think there is any signal loss in our analysis. What still left is that we need to account for direction dependent calibration. Also, recent studies show that the time correlated gain error has a significant effect in the H1 power spectrum. That needs to be taken care of. Also, there is a polarization leakage variation of beam that needs to be understood for UGMRT. And we also have a EoR data set for 120 to 250 megahertz, but there is no beam information yet, and the RFI scenario is extremely bad. So as you can say that for band 2, there is no no parameters is being quoted by GMRT people. So this is the primary parameter for as model as a polynomial. So I will stop here. Thanks.
Thanks a lot, Arnab. So yeah, if you have question, Slack is open for that. And we will move straight away to the last talk of this session, which will be by Isabella about foreground subtraction with sparsity-based method. The floor is yours, Isabella.
Yeah, thank you. So hello, everybody. Can you see my screen correctly?
Yes.
Okay, great. Let me start. So yeah, I'm Isabella. I'm based at lab at CA, close to Paris. So I will show some works on foreground subtraction that I've been doing with Melis Irfan and Jérôme Bobin here at SACLE. It's based on this paper. So all the plots that I will show without the citation, they belong to this. So it's about maps in intensity of the 21 centimeter, but a lower redshift than the EoR. We call it the post-EoR signal, and we care about it because it's a signal that traces the large-scale structure in the universe, so we can do cosmology with it instead of looking at the single galaxies, so in a usual galaxy survey. So this is why we are interested in the signal at the lower redshift as well. So what I will say will apply to EoR, but I will focus on this in my exercise. And this is a list of the instruments that are already looking at this signal at these redshifts or will be looking. So just to see that there is a momentum also in this setting case. So let me jump straight in the problem. Many people already said and talked about the foregrounds. This is a plot of our simulation. So this is the brightest temperature of these very bright foregrounds with respect to blue. Here is the signal. So as Josh said before, the usual way of getting rid of foregrounds is considering the fact that they are smooth in frequency compared to the signal, so they can be filtered out with different techniques. Although the picture is not that simple because there are mode mixing components, as Bharat said in the very first talk, that can corrupt this picture of the smooth foregrounds in top. Like here I'm showing with this pink line a model of polarization leakage. So due to the non-perfect calibration of the instrument and not perfect knowledge of the beam of the instrument, as you can see, it starts to behaving non-smoothly in frequency, and this is a problem for standard component separation techniques. Moreover, this is just for one line of sight, but this polarization leakage model that we have been using, actually, due to the magnetic field of the galaxy and the complex structure of Faraday rotation, actually, we expect that it will behave differently at also spatially, look at different line of sight, looking at different direction in the galaxy. So it will be a complete mess for standard component separation methods. So this is, so let me start with what we have been doing. So we have been trying to work with the simulation with the foregrounds as realistic as possible. So the galactic ones from the black sky model, and then some extra galactic contribution and the polarization leakage that I've been telling you about. This is how the signals should look like, what we have been looking for, just to see the difference in also not only in the frequency domain, but also in the spatial domain. And this is something that will be crucial for our method, because indeed it's based on sparsity. So what is sparsity? So a signal is sparse in a representation when we can describe it with the least possible coefficient as possible. So for instance, the classical example is Fourier space for sine waves, for waves, in which you, for a sine wave, for instance, you need just one number in order to specify it. So if I manage to find the base where all my sources are sparse enough, then I know that their mixture will be less sparse than, the mixture will be less sparse than the sources to begin with. So, but I can reverse the problem and look for the sparsest solution that's possible to disentangle this mixture. And this will help me at separating the sources. So where can we enforce sparsity if we think about our foregrounds? Well, not in pixel space. So this is the histogram, how, for instance, the synchrony looks like in pixel space. But if I move, if I can represent these foregrounds in wavelet space, things start to look better in a sparse sense. Of course, there is not the ideal picture of just few coefficients and everything else is zero. It's more complicated, but still, because these coefficients are less in number, it's easier to disentangle these components. So this is the trick. And of course, all related to an overall sparsity threshold that is related to the noise of the mixture in this domain. All I said is compactified in this minimization function that our algorithm uses. It's called GMCA. Where so after I linearize my signal in an unusual linear way, so the mixing matrix times some sources, I have this minimization function where together with the usual data fidelity term, I have this minimization of the components in wavelet space. So, and then we iteratively find A and S by satisfying these two conditions at the same time. And this is the recovered foreground that we get. It looks amazing, sub% level, but indeed, we really need to recover really well the foregrounds. The signal is so small that I mean, the precision that we need to get in performing this has to be really high. To be a bit more quantitative, here I'm showing the relative difference of the angular power spectrum that we cleaned compared to the true one. For in like these three panels correspond to three different scenarios where I cut the simulation in three different ways, more channels or less channels. And I can see that the more the channels, the better for the reconstruction. Already with just three sources, I get less than 2% bias on the angular power spectrum. And indeed, if I look at one single channel, for instance, here is the angular power spectrum in blue of what I would like to retrieve, the cosmological signal and the noise. And the orange crosses is my GMCA residuals. And here are the residuals of the cosmological noise that has leaked in the foregrounds and the foregrounds that have leaked in the cosmological noise. So these are under control if you see the scale here compared to what I'm looking for. This just one channel, just looking at one channel, but using all the 200 channels to get my answer with the GMCA. If I do the same exercise with less channels, I start seeing that there are some problems. I have more foreground leakage. So it's really not the thickness of the channel that matters here, but the how many channels I have. So how much data. Indeed, this is something that also we find in the radial direction. So this is the power spectrum in frequency space, the same sort of statistical estimator here. As you see, just with three sources in this 200 channel case, I retrieve a very good line of sight power spectrum for scales above 0.05 inverse megahertz. And one thing that we looked at was also RFI. So as we heard, well, everybody here knows about what RFI is. For instance, here I'm showing a picture from, this is some data from the MIRCAT, from MIRCLASS, so the intensity mapping survey with MIRCAT. So this is a time as function of frequency. You see the flagged area here. So we tried in this exercise to work with the same RFI flagging that was done with MIRCAT. So these are the three scenarios that we have been playing with: a symmetric and asymmetric one, and this one that look a little bit more than true data.
Yes, 3 minutes.
Great. So since GMCA works better with as many channels as possible, we try to feed GMCA the full data cube, even if there were all these channels missing, instead of feeding the algorithm with 2 different data cubes. And these are results that I mean, we were really surprised how good it is. So on the left for GMCA, here the relative difference in angular power spectrum, and on the bottom in the line of sight power spectrum. And you see that we recover, this is with still with the 3 components, we recover really well again. The results is not the same, for instance, for an independent component analysis technique, where, I mean, having RFI seems to be a problem. Here on the left, we played with fast SEA with 4 components and 5 components, including polarization leakage. Well, things are not that easy as we expected, but still we can recover, like here on the left, a pretty flat power spectrum with some bias up to some scale cut in L. If I know where this polarization leakage is behaving more badly, let's say, I can mask this region and try to push this limit, although I need to use a larger number of sources. This is the comparison with the fast SEA as a comparison. And here again, the same sort of plot with the polarization leakage, where I just plot 1 channel just to see what's happening. So here with 6 sources, I can recover my cosmological signal power spectrum up to L100, for instance, but then I see that the foreground leakage starts to be dominant. But on the other hand, if I increase too much the number of sources, the number of components that I'm removing, yes, I can push the reconstruction up to lower L, but I see in this red line here that the leakage of the signal in the foreground part starts to becoming important. So we need to find a compromise in this. So these are my conclusions. GMCA seems to work very well at estimating the angular and the radial power spectrum with these limits. We were the first one to start to look at more complex component in the data, and we realized that it's really important to start doing so when we test these techniques. But we were really happy that at least in the RFI case, it seems like things are under control, and we can use all the data cube even with the missing channels. And I want to leave you with a bit of perspectives. These are some of the things we are thinking about or we are already working on. So my results so far have been full sky, what I've been showing, but now there are some studies on patches. So according to the region of the sky you look at, there are different levels of sparsity, so GMCA behaves differently. Now we're looking at the effect of the beam, so with the different side lobes, how we can take care of it. We are starting to, since GMCA is a multi-scale approach, we're starting to, for instance, using a different number of sources according to different scale, and this looks promising, like it's helping the reconstruction. And last thing, GMCA is a blind method, so there are no priors except the sparsity one, and it works in the image space. So sparsity is imposed on the image. But we do have some priors, we do have some knowledge in the harmonic space or in frequency. So it would be nice to couple GMCA with something else in this sense. And I'm done. Thank you.
Thanks a lot, Isabella. And thanks everybody for all the speakers for this session. I think, Adeli, we have, or Suman, we have a few minute break now. Yes.
Yes. So then after,
yeah, in 10 minutes, I think.
Yeah.
Okay. We need to get 10 minutes for the discussion session. See you.
See you.
Okay. We start in 2 minutes. All right, so maybe we can start again. All right, so we had a quite full session this morning, covering a lot of topics already. But I will remind you that there is also posters and recorded talks, and which are advertised in a specific channel in Slack. So for the recorded talks, you can look at the SIP 21 centimeter recorded. And for the poster, look at the SIP 21 centimeter poster, and you can look for the talks and posters and ask a question there. And there will be a special session at 10 a.m. Universal Time for questions for the recorded talks and posters on the dedicated Slack channel. So if we look at all the contribution from this session, so we had 7 live talk contribution, but there is also 1, 2, 3, 4, 5 recorded talks that you can look at, and 2 posters, and they cover quite different topics in the observation of the 21 centimeter signal. And I looked at how the different topics. So I looked at the abstract and I tried to look at the most significant words in this abstract. And of course, 21 centimeter signal is one of the most frequent word in there, but not surprisingly, also foreground is quite high in this list, and it's of course one of the things that is bothering us a lot. Here you have also effects. You have many effects, RFI and instrumental effects also, which we have to deal with. Calibration is high in this list as well. Systematics, of course, but you have also some words like progress, which appear also quite high in this list. So it shows that we are making quite some progress in the field as well. So I tried also to divide the different talks in the different epochs they correspond to. And if you look at the cosmic dawn, so there is three contributions on the cosmic dawn, and they are which are targeted principally at the cosmic dawn, and which are mainly global signal experiments using SARAS 3 these two contributions here, and the future reach experiment here. Of course, you have a lot of talks on the epoch of ionization itself. Talks also which cover both the cosmic dawn and the epoch of ionization, like EoR, which will cover also the cosmic dawn with a new receiver. And we had also three contributions looking at post EoR 21 centimeter signal by Isabella Arnab. And Shrila also is at higher frequency than the epoch of ionization, but it's a contribution which look for the foreground at this frequency, but to constrain the foreground of the epoch of ionization. So if we look also at observation versus simulation, so of course most of the contribution about observation using a different instrument. You have a few contributions mainly on simulation, and of course it's quite a complex experiment, and so simulation is needed to test new technique, to test new pipeline, and to look for alternative estimators, what we can gain from that, and also to look at the impact of some contaminants, and so several of these of the contribution we had today look also at comparing the simulation and the observations that they have, so that they can try to understand better what is observed and try to deal with the systematics a bit better. Then if you look at the different challenge of the 21 observation of the 21 centimeter signal, of course the foreground is at the top of the list, and you have several contributions which look in detail into trying to deal with this challenge. And then if the other big challenge in the observation of the 21 centimeter signal is trying to correct for the systematics and with calibration. And so here you have also a lot of contribution which look into this aspect a bit more and try to find new ways to deal with this systematics better. And now, if we divide these different talks in the different instruments that they use, ERA is also you have two contributions that use ERA data or ERA simulation. 3 contributions for LOFA, 2 contributions also for GMRT, 2 for SARAS2, and you have also REACH also, which is a next experiment, and NENUFA also. The mistake here is NENUFA, and Pratouche, which is space quite promising, also a space-based experiment. And with this, I will open this session for discussion, and if you have also any question for the speaker of this morning, you can also tell them now. So I don't know if anybody has particular topics to start with this session that we would like to discuss about. or if anybody has a question about the talk of this morning, which have not been answered on Slack. Okay, so
I can maybe
I will start with a topic for discussion about the alternative estimators of the 21 centimeter signal. So we had a talk about 1 point estimators this morning by Pianat. And so Pianat was asking in this conclusion, whatever it was going this way. So I don't know if Pianat, maybe you can ask a question again, or you yes, no.
Can I say something?
Or if anybody wants to comment on this aspect. If whatever, I think the answer of using the skewness, for example, is worth it. But if somebody has some insight on this, or Isabella want to raise hand? Isabella.
Yeah, can you hear me?
Yes.
Can you hear me? Oh, okay, great.
Go ahead.
Yeah, okay, just to, actually I will change topic, but I was curious about the people that use foreground avoidance. Won't there be always some foreground leakage even in the foreground safe region? Like, can you really avoid altogether foregrounds? And I mean, I guess no. So how do you really estimate the leakage of foregrounds in the region? Like just
I don't hear anybody actually now. Okay, does that work now?
We can hear you, Florent.
Oh, okay. No, that was on my side then. I don't know, sorry.
But I could try to take part of that question. I mean, certainly there's foreground leakage is sort of an unknown in the sense that there are things that we see that are obviously foreground leakage, right? We don't see that the precise mathematical line associated with the horizon. Outside of that, there's nothing. And we definitely see other systematics outside of the horizon as well. So, it's about finding ways to diagnose those. So the question is, are the foregrounds that we're seeing, or things that we're seeing outside the wedge, can we understand them? And a part of that is just digging down deeper. So, for example, on the polarization question, we've certainly seen high RM galactic pulsars. We've seen at least a couple of them, and they showed up as polarized, as spectral emission in our individual polarizations, and then when we formed Stokes eye spectra, they more or less went away. But there should be a leakage at some level, so we can use the fact that we see them very clearly. Talking about polarization, we see them very clearly in Stokes eye. In instrumental polarizations X and Y, or north and east, or however you want to think about it. The fact that we see them so clearly there, and they mostly go away in I, if we then see excess power there in I as we keep digging down further, that's a sort of null test that you can do, where you can sort of chop the data up into different parts and say, is there, if we're detecting if we're quote unquote detecting the EoR only at certain LSTs, we should really ask ourselves the hard question of why. So those are the kinds of strategies I think that can help us build confidence that we are seeing, if we're going to make a claim about a detection, that it is really EoR and not foreground leakage.
Could I ask a question,
Yes.
which is more? It's slightly more general. So in preparing and planning the various observations, people have used simulations to sort of to see if the strategy chosen is good. So the whole foreground avoidance, it was, I guess, based on a theoretical calculation which showed this, which worked very beautifully. For LOFAR, we tried different foreground removal techniques on simulated data, so including this GMCA and FASTICA, it worked beautifully. But then when the real data came, it worked much less well. So I'm wondering, so in general, I guess we have certain expectations based on simulations, which then not always come true when the real data is there. I wonder if some of the observers could reflect on this topic and what we can learn from this for future measurements and future experiments.
Of course, it all depends also how complete is the simulation you are using, and if it's complete enough to the problem you are trying to answer. And I guess, early on we were not having simulations that were covering all the systematics that we found later in the data. But I think there is quite a lot of progress on getting more realistic simulation.
I think in addition to that, it's also very important to validate if your simulation pipeline and analysis pipeline introduce additional systematics into the data. It's very seriously. One of the paper that will come with the upper limit paper is the validations of the analysis pipeline itself, and we make sure that there is no signal loss or systematics, unknown systematic introduced by the pipeline.
Yeah, I also think there is still a lot of work to be done at the level of, I mean, there are systematics that we cannot simulate, but I mean, I'm really surprised, for instance, for the single dish simulations, how few people simulate a real beam instead of a Gaussian one. And that we kind of know how the side lobes should look like. So there are things that we can do now in terms of simulating systematics, and not so many people are doing at the moment. So there is room for improvement to get simulations that are closer to observations. So to understand why methods are failing, are not as successful as we would expect them on real data. So I think there is a lot of room of improvement, something that can happen soon, and something else like this leakage that I presented. I mean, there are just a couple of models around it. I mean, it's really, we don't really know even how to model it. So that is also another question.
I want to just +1 to that. Like, a simulation with a Gaussian primary beam is not worth a lot. At minimum, an Airy beam. It doesn't go to 0 quite so quickly.
Is it all right if I pose a different questions? Or?
Yes, go ahead.
Yeah, and this is a different question than the one that I posed in my talk. So we've seen a lot of new uses in experiment based on machine learnings, but as an observer, it's very hard to convince me, and I guess as an observer, to believe that what the machine learning do is correct. Yes, it seems like it's working sometimes quite well, but you know, like when you do the analysis on observation, you do it based on signal processing mostly, and so we understand what's going in there and why it's come out like that, and that is not the case with machine learning. So, what is your opinions on the machine learning algorithm? Is there a future for it? What need to be done to make it the future?
I think it has also to do with simulation, because we usually used simulation as a training set, and if simulation are not realistic enough, then you can get biased result from this algorithm.
So I think it depends on the machine learning algorithm you're looking at. There's like in recent years, there's lots of advance in using kind of semi-supervised, self-supervised methods that can supplement the supervised training. So it's important to have kind of, I mean, I guess it's important to have both. So you have the supervised that Flora was mentioning, where you need a really good training set. But you can also do semi-supervised training, for example, where you, let's say you take your image, you encode it, and you get like a latent space, as you call it, where you can, for example, try to tweak this to get like physical properties out of that. And then you decode it. And that's kind of how you learn. It's just an example. But you can have some methods where you don't really need a simulation training set. And I think those together can work really well in the future. But I think that's a really new progress like right now.
So you mean to try to extract some information that you would not think of analytically, for example? Journey.
Yeah, exactly. So you can basically have like new architectures that don't need to be fully supervised, but they, of course, they need some measure. They need some distance measure or whatever to say, okay, for example, this is like an anomalous part of the data that's very different from the rest, like to flag something or so. But they start to be really good at that as well.
So if nobody else has a topic for discussion.
Maybe I can advertise. So in the afternoon, we'll have, I think, 2 or 3 machine learning talks for the theory side, which also connects, of course, into the simulations. So maybe that fits in there.
Yes, thank you.
So out of curiosity, to do imaging of the EoR, should we wait for SK or something will happen before that with the other instruments? So not power spectra, but images.
Can
I don't know. Hmm?
Can EoR do it?
We are hoping to do cubes of filtered EoR. Now, when you wedge filter a 3D data cube, it becomes much harder to interpret. But there is still some information there, and perhaps with some kind of clever machine learning like we saw this morning, there's a lot of information there, though those results looked almost too good to be true. So I'm very curious whether, very curious to see the paper. But yeah, I don't like, in terms of the kinds of things that have been promised of these beautiful 3D maps of the universe, I don't think Hera's the right thing to do that. If we could tell you the amplitude, that's a great start, right?
Yes.
Yeah, I feel like it's about the map making. Once we can make detections of the imaging power spectra, because in principle, right, it's making a map. It's basically once you have visibility gridded onto the K-space, you can make a map. And if you know the beam variable, I think the most challenging parts of map making is knowing your beam. it's going to be that.
On the imaging question, can I turn that around on the LOFAR folks, or if there's any NWA folks who want to talk about that? Because if there is the raw sensitivity there, and of course the foregrounds are an enormous challenge. What's your sense? Do you think you need to wait for the SKA and everything is a training run for that?
Well, I think for LOFAR, the sensitivity to get images is very marginal, and I think we'll have to wait for SKA to have very something.
Same for the MWA. I mean, you'd have to really basically have a perfect instrument in order to do it, and you know, just the logistics, the reality of an instrument is that it dies slowly in weird ways over time, and it's just impossible to catch all the little bugs at this time.
So SKA, as it's designed, is an incredibly complicated instrument. Is it reflecting those sort of hard on the ground lessons of MWA and LOFAR and Hera?
I think that's a question that remains to be seen. I think yeah, but
go for it, Nicole.
Say that again.
I just say go for it.
Oh no, that was all my comment. I was just being pessimistic as usual.
So I'm trying to understand what you Nicole and Florent just there. So does that mean that the challenging part is keeping the instrument stable enough so that you can integrate long enough for sensitivity?
Well, if you look at the noise that you get in your image, if you want to get image of the signal, you need to accumulate a large amount of data with LOFAR. So that's the limitation, basically. Yeah. So it will be difficult.
And the promise of the SK is that it has so much collecting area that you wouldn't have to integrate long.
So yeah, the collective area is much better.
I see.
Oh, that's the sensitivity is it's so much better.
Also, the UV coverage is much better, right?
Yes.
So it's a combination, I think. Well, that's what we hope. Then the antennas are more complicated, which I think is the contentious issue with the SKA.
Yes.
Which we don't really know how that will affect us. I mean, that's well, the expectations, and they're positive, but I guess reality and expectations are not always the same. Yeah.
So how does one actually demonstrate that, for example, the direction-dependent calibration that's being used for LOFAR, like how does that apply to SKA? It seems like you would need more facets or whatever to break the sky up.
Well, the primary beam is not so different. So, well, I think the main difference with LOFAR is that you will be the maximum baseline. So the resolution that you will get to make this sky model. But you can also get sky model from GIM catalog, for example, to complement that. But there will be a lot of lesson from LOFAR MWA that will go into SKA. That's clear.
There's a question in the chat.
Yeah,
mega constellations. I don't know if anybody wants to say anything.
I don't know if anybody has some insight on so the question is about mitigating potential contamination from a mega constellation of satellites, which is which will be an issue for a lot of radio experiments.
Well, I know that for Mir class observation satellites are already a problem right now, so it can just go worse, I guess, with the increasing numbers of them. Yeah, actually, it's a problem that is worse than expected.
So for what kind of observations?
For intensity mapping at frequencies 900 and above.
Okay.
Are there, with the exception of the Orbcomm satellites, anything planned in the 21 centimeter EoR cosmic dawn band?
I don't think so, right? These satellites are mostly for wireless communication, so they usually go to higher frequencies.
I think probably a few gigahertz, I suppose.
I think there's a very small band of military satellites. We know nothing about them for good reason.
What's the problem with the mega constellation is also the reflection, which maybe can be an issue.
I think there are negotiations with at least some of the companies to turn off the emitting signal when they pass over the SKA sites. So that should mitigate it somewhat. In general, I think the lesson is, even though we would probably all want to shoot down the satellites, we try to behave very civilized towards the companies, because then they're actually more, hopefully, well, they seem to be more willing to help us with things. Apparently for the optical, they've, for example, experimented with low reflection coating so that they don't reflect as much light. And that was done because, I guess, of so talking to astronomers and keeping an open channel there. I think SKA is trying the same thing.
Can we actually use them to do beam mapping and calibrations? I know we have, like the MWA has used Orbcomm satellite to do that before.
We have just completed pretty extensive beam mapping measurement for the MWA. And so this was 14 tiles at both polarizations and multiple pointings. And so it has revealed interesting stuff. And also what it's shown is that it can be a monitoring system that works in parallel to other observations. So you passively, you collect satellite data and over time build up maps which can then be used. But the problem is it's narrow frequency, so you don't have broadband information. So some of our thoughts are that you would use these high resolution satellite maps as a base and then use drone broadband measurements to validate extrapolation to other frequencies.
Which satellite are you using for this study, Aman?
So we're using the Orbcomm satellites plus the Meteor and NOAA weather satellites. And I think the Meteor satellite was surprisingly bright and much more broadband compared to the Orbcomm ones.
Okay, it's already 9:30. I don't know if we close the session here, Suman, or if
yeah, actually, Adley has already sent a message to everyone for a conference photograph. So we would request all of you to switch on your camera, though means most of you are not visible right now. Yeah. So please do so that at least we can take a screenshot. And as there are, I think right now 52 participants, so it will be multiple screenshots because I can't see all of you in the single window. And before we take the screenshot, there are two small announcements. One is that Rajesh Mondal is also part of this organization team. He had helped us quite a lot in organizing everything, but because of some unavoidable circumstances, he could not be present today. And the second one is about the next SAZERAC SIP, which is CIDER. So it's called ISM during the epoch of reionization, and this is being organized by Maria Emilia De Rossi, Peter Lawson, Christopher Lovell, and Ashwin Vijayan. It will be on 24th and 25th February between 1600 to 1830 UTC. So that was it. I still see few blank screens. If all of you could switch on the camera, then we can start taking the screenshot.
Cheers.
Yes.
All done. Thank you.
Well, thank you, Adeli. And well, with that, I think we can close the discussion session. So thanks a lot for everybody for the nice discussion and for the speaker also. And well, the discussion can continue on Slack, of course. It's quite active, so that's quite nice. And well, Adeli, I will leave it the last word to you.
Okay. Thanks, Floran, for chairing this session. And please go to the Slack for the recorded talks and posters. Yeah, thanks. And we will meet in the second session. Thank you. Bye.
Thanks so much.
Bye. See you.
Thanks.
Thank you.
Thanks for being here. Maybe at least stop the telecast in the